All right, well, we are in lesson 6.5, where today we're going to talk about a new family of functions. Um, I have written here on the screen just a review of the functions that we've already done. We've spent time with the linear function. That's mostly what Algebra 1 is about. And we do hit on the quadratic at the very end of Algebra 1, but the majority of the time we spend on linear. And I've written the parent functions in the middle. So the functions that are kind of like the most basic type of that function. So we know linear, the parent function is y equals x. It's going to take this straight line graph. We have absolute value, which we did at the beginning of the year in Algebra 2, which is y equals the absolute value of x, and it always has this V shape to it. We did our quadratics. Like I said, we did this in Algebra 1 at the very end, and then we've done a lot with this now. And that's your U-shaped graph. The highest order will always be squared and x squared on that one. And then we just finished our cubics, which is the highest order there is x to the third power, and that takes kind of like that S sort of hooked shape. So those are the ones that we have done. I'm going to use the absolute value function to just review how we translated things on the graph based on the way that the function is written out. And so in red here, I have the parent function, y equals the absolute value of x. So that's going to take that V shape where it runs through the 0.11 and then comes over here and runs through the point -1, 1. All right, so this is the absolute value of x. If we were to change that and we wanted to add 2, so in green we have y equals the absolute value of x plus 2. So if we remember when we had that plus 2 on the outside of the absolute value symbol, that gave us vertical shift, and the plus 2 made us go up 2 units. All right, same slope for this one on those individual lines, but we're just shifting that graph up 2 units. If it had been the absolute value of x minus 2, then we would shift down 2 units, and it would have the vertex at -2. For the orange graph, in this particular one, the 3 is on the inside of the absolute value symbol. So we have the absolute value of x minus 3. So since that 3 is sitting inside the absolute value symbol, that gives us the horizontal shift. All right, so in this case, that horizontal shift is going to take us over to +3 here. Again, we have the same slope on each of those sides of the V. We're just taking that parent function, that red one, and sliding it over to the right 3 units. If it had been the absolute value of x plus 3, then we would have shifted it to the left 3 units, and it would sit at -3. For the light blue, we have y equals 3 times the value of the absolute value of x. So now we have an a value that is greater than 1. All right, so the a value was the one that in that formula. Okay, so here's our formula. The a value is the one that sits out here and determines how steep the slope of the line is. So this one's going to sit on the origin, but it's going to rise at a much steeper clip. So it's going to be, instead of going through the 0.11 over here, it's actually going to go through the 0.1 -3. And I probably should have written that in on my graph, but I'm just going to do it right here. All right, so that would probably go through, it'll just go through a lot steeper. All right, on both sides. I'll try to mirror that here. All right, still has the V shape, but is rising a lot quicker. And then in light green, we have the opposite of the absolute value of x. So again, that has an absolute value, or I'm sorry, an a value that is less than 0. So that means that we are going to have an inverted v. So it's going to have the same slope as the red one. This is exactly the same as the parent function in every way except it's inverted. Okay, so what I want you to do before we do the work on the worksheet is I want you to use your calculator and plug in these 5 equations that I have written here. I just kind of want you to play around with the calculator and kind of see what these look like when we do the vertical and horizontal shift, and when we have shrink and stretch, depending on what the A value is. Just backing back up though, I just in general put the 2 new function families that we're going to learn in this section. So you're going to have your square root function, which is what I have down here in these 5 equations, is the square root function. You can see that the red number 1 down here that I want you to do on your calculator matches the parent function up here, y equals the square root of x. And it's going to take this shape that's just sort of like a half U shape. The cube root function is the other one we're going to do in this section. And I haven't given you any examples of that to put on your calculator down here. But that one is going to have that S sort of shape that looks familiar with the cubed, the functions, the y equals x cubed that we did in the last chapter. So that takes on that similar shape. So if you look at on page 446 in your textbook, you can see the parent functions graphed out for these two. But go ahead and follow my the directions for the calculator. You probably aren't going to need my directions after you get past number 1 or 2, but I tried to put in the parentheses for you where they need to be in order for these to actually graph correctly. Number 3 especially needs parentheses around that x plus 2 so that that whole thing gets graphed under the square root symbol. There are 2 sets of directions. That's why I've got the word or in here. You can do it either way, and both of them will work. Probably the second way is maybe a little bit quicker. So just pause the video and take a few minutes to get these graphed in and just get familiar with what these are going to look like. And so over here, I'm just using the graph on number 9 to show you roughly what these graphs should look like when you plug them into the calculator. So we can see that red is that parent function that is starting at the origin and runs through the point 1, 1. The green version of the graph is the parent function shifted up 2 units. The dark blue one is shifted to the left 2 units. Number 4, the orange one, that is the parent function, but the A value is greater than 1. So we have vertical stretch on that one. That means that it's going to be rising faster. So you can see there it is not going through the point 1, 1. It's actually going through the point 3, 1 right here. Okay, so it's rising up 3 units every time it goes. For that first point, it rises up 3 units and goes over to the right 1 time. And so you can get that first point there using that A value. And then the light blue is exactly the same thing as the parent function. It's just inverted into the lower quadrants. So you can see that I've written out our formula. So all these functions have formulas. This is the formula for the square root function. And it's all the same letters that you're familiar with from some of the other functions. Our A value here is going to tell us whether we have shrink or stretch. So if the absolute value of A is greater than 1, which that's the case in our orange graph, then we're going to have vertical stretch. If it's less than 1, we're going to have vertical shrink. So we're going to see it rise. It's not going to rise as quickly as the parent function. It'll actually rise a lot. It'll rise lower than that. We don't have an example of that one in these 5. If A is less than 0, like we have in the light blue down here, number 5, then it's inverted. So it's upside down. B tells us the horizontal shift, just like it has in a lot of the other functions. And C tells us our vertical shift. So notice just like with our quadratic formula, we have a subtraction sign underneath the square root symbol, and we have an addition sign outside the square root symbol. So if we always have to make sure that the function is in that form, as a difference under the square root and as a sum outside of the square root, so that we can make sure that we get those the horizontal and the vertical shift accurate. Okay, so now let's look at some of the problems on the worksheet. In 1 through 3, we have to graph the square root function, and then we're going to state the domain and range of that function. So going back to let me go ahead and write out our formula. Again, make sure you've got this in front of you. So this is our formula. If we look at number 1, we can see that we don't have any horizontal shift to the right or left because we just have an X right there underneath the square root symbol, but we do have a -2. All right, but this actually needs to be rewritten as a sum because the formula states that it has to be plus C. So if we rewrite that as a sum, then we can see that we will have plus a -2. And so that means that we are going to be shifting down 2 units to -2. We're shifting down from the origin. And then that will actually run through this point right here because of the A value is still 1. So up 1 over 1, we can get that first value. So that will look like this. So we can, if we recall that our domain is all the X values that satisfy the function, then we can see that since our X's are starting right here at 0, at X of 0, then we want all of our X's to be greater than or equal to 0. The range is all those Y values. So the Y values start down here at Y of -2, and they're going to run, since the graph is going this direction, all of your Y's are going to be greater than or equal to that -2. So there's the domain and range on number 1. For number 2, we have a horizontal shift of 2 units because we can see right here that our B for the formula is 2. It's written as a difference under the radical, and so that's the way we want it. So we're going to shift it over from the origin. We're shifting it over 2 units. Again, the A is 1, so we know it's going to run through this point right here, and it'll look like that. So now our domain is going to change a little bit because we don't have any X's that are going to be less than this 2 right here. So X has to be greater than or equal to 2. And the range is not going down at all. The Y's aren't going down at all into the negative quadrants. So, that should be Y. All the Y's need to be greater than, not less than, greater than or equal to 0. In number 3, we have a horizontal shift right here. That needs to be written as a difference. So instead of +1, it's minus a -1. And then we also have an A factor of 3. So our A is greater than 0. So we know we're going to have a vertical stretch. So we're expecting this to rise faster than the parent function would. And so we're going to be shifting this over 1 unit to the left. That's what that -1 tells us there. And now we're going to be rising for that first point after our initial point here. We're going to be rising over 3 and to the left 1. So we can see that this is going to have a much steeper start to it. Domain here would be all the X's to the right of our -1. So X needs to be greater than or equal to -1. And the range is the same as number 2. There are no negative values. So our Y is greater than or equal to 0. And I want to make one correction here to the formula before we move on, just because I want to make sure I'm using the same variables that the textbook is using, and instead of using B and C, they're using H and K. So let's just keep it consistent with the textbook. It's the same, of course, same idea, just different variables. For the cubed root, which is what we want to do down here on 7 through 9, it's the same type of formula. So in this formula, You just have to have the cubed root sitting in there for the index. But it's going to follow the same principles. And let me stick the a in there. I left the a out. Okay, so here's your formula for the cubed root. And so number 7, they give us the cubed root of x plus 1. So we can see that we're not going to have any horizontal horizontal shifting. We're going to have vertical shifting. It is written as a sum, which is what we want. So we're going to shift up 1 unit. Our a value is 1. And so with the cubed root functions, we can go up 1 over 1 for that first initial point up, and we can do the same thing down 1 and over 1 here to get those 3 points. Now these are, at least I think they're a little bit more challenging to actually draw the curve in. So, but they take the same shape as our x cubed. They'd have that kind of S looking shape. So this is not a straight line. This is not linear. Those points almost look like you could make a linear graph out of them, but it's a cubed root function. So we have to turn it on its side. So it's on the side instead of the way the x cubed was upright. This is going to be written horizontally instead of vertically, and it's going to have that nice curve in it with those 3 points right there in the middle. All right, number 8, we have horizontal shift. We have an x minus 4 under the radical. It's written as a difference, so that lets us know that we need to shift to the right 4 units. And the a value is still 1, so I'm going to go up 1 to the right 1 from my original point, and then I'm going to go down 1 to the right 1 as well. And then I'm going to do my best to draw in that curved line with those 3 points. Number 9, we don't have any horizontal shift, so there's no h value under the radical. The k value is not there, so we know we have no horizontal, no vertical shift, but we do have an a value of 3 now instead of 1. So what we know here is that this is going to rise on the one side faster, and it's going to lower on the left-hand side a little bit quicker. But we're still dealing with the parent function, so that means that it is running here through the origin. We're not shifting left or right, we're not shifting up or down, but we're going to go up 3 to the right 1 to get that point, just that first point, and then down 3 to the left 1 to get that next one. And then draw in a curved line. So because a is greater than 3 here, we end up, greater than 0, we end up with vertical stretch. So 13 and 14 are dealing with a speed of sound problem. The speed of sound in feet per second through air of any temperature measured in degrees Celsius is given by this function. So the v is the dependent variable. Okay, that's the speed of sound. And what is it dependent on? It is dependent on T, the temperature of the air. So the speed of sound is going to be determined by what the air temperature is at any particular time. They ask us to identify the domain and range of the function because they want to draw out this idea of the square root function needing to be limited to only numbers that are greater than 0. Okay, so you can't, so your domain for a square root function has to be x greater than or equal to 0. Because if we don't have it as x greater than or equal to 0, we're going to get into the square root of negative numbers, which is not what we're dealing with right now. We want to limit that domain so that so that the radicand underneath, the number underneath the radical is greater than or equal to 0. So in a problem like this, when they ask us to identify the domain, we can take that t plus 273 that's under the radical symbol, and we can say we definitely need that number to be greater than or equal to 0. And so because we know that, we can solve for t, which is with a simple subtraction problem. And so we know that t has to be greater than or equal to negative 273. All right, if it's any less than that, we're going to end up with a negative number under this radical, which is a problem. All right, so here's your domain. And then your range can be, V can be anything greater than or equal to 0. All right, so we're talking about speed of sound. So we don't want to go into the negative values. And so we just need to limit that to anything greater than 0. And then in 14, they specifically ask us what the temperature of the air is if the speed of sound is 1,250 feet per second. So they're giving us our V right here. They're giving us the dependent. So they're saying if the speed of sound is 1250, so I'm subbing that in for a V out of my formula that I'm getting up here out of the problem. They want to know what T is. Right, so we have a radical, we have decimals, we've got a lot of good stuff going on here, but just follow your rules for solving a variable. Do one step at a time. Do the first thing that you know is right in this problem. And you know the first thing that we would do in a problem like this is we would need to get rid of the denominator. We're going to do that by multiplying both sides by 16.52. All right, I'm going to put that in parentheses as well. We'll get this large number on the left side. This 16.52 denominator will go away, and we'll end up with this right here. All right, because we're multiplying 1087 by this radical, that we can undo that with our division. Those go away, and you end up with 18.98. and this radical. And we learned a couple of chapters ago that in order to get rid of a square root symbol on either side, or on one side, we can square it. So if I square this side, then I need to square this side. All right, the exponent 2 and the square root symbol will cancel each other out. 18.98 squared is 360.9. And then we can just simply subtract to solve for our T, and that will be 87.9 degrees Celsius. So that's our final answer. When we have an airspeed, a speed of sound of 1250 feet per second, the air temperature needs to be 87.9 degrees Celsius.